I thought it's like not the same way.
Okay, chapter 2, page 38. Today we will learn a number of tricks allowing to design isotropic distillation flow sheet. Cross the distillation boundary. Previously, you would not be able to do it. Chemists cannot do it either. And you learn the tricks well, you can, like Mr. Lee Parton, Purdue University, he filed a patent reducing 9 separated to 1. Eastman, alkyl acetate. Okay, let's review this. 238. Suppose you have a triangle. Vertex is pure component. Binary azeotrope, ternary azeotrope. So, if this is the pure component, you have a residue curve from low boiling to high boiling. This is the curve. This is a pure component. We call this a node. So, N1 node with 1 component. Now, if you have low boiling component, this goes to high boiling component. This all goes out. This is also a node with 1 component. How about saddle? Low boiling, high boiling, intermediate boiling. So your RC goes that way, bypass intermediate component. We call this saddle with 1 component, S1. The other way is low boiling, intermediate boiling, high boiling. Your RC goes this way. This is also a saddle with 1 component. 1 refer to pure component. Binary azeotrope. How about this point? this on the triangle, this is the high boiling component, all RC merged into here. So this is node, but with two components called N2. This on the side of the triangle, low boiling going to high boiling. This is node, two component. Whether it's stable and stable, I don't pay much attention, but in Aspen, you see the word stable and stable. Here, low boiling, intermediate boiling, high boiling. So your RC goes this way. This is a saddle with two components, binary azeotrope. Okay? Now, low boiling, intermediate boiling, high boiling. This is a saddle, S2. Why do we try to learn this? We want to understand this, apply verification equation to make sure you have drawn the correct RCM. Ternary azeotrope in the middle of the triangle. This is the highest boiling ternary azeotrope, this is lowest boiling. We call this N3 component. And this is the minimum boiling azeotrope, still N3. The last one is a little tricky. This intermediate boiling ternary azeotrope, RC goes this way, RC goes this way. Make sure you connect this ternary azeotrope to component binary azeotrope. Two arrow goes in, two arrow goes out, two in, two out. Here, two in, two out. So with this, let's look at one example. This 241. You look at the 62.1, 100, 70.8, 82.8, 66.7, 78.5. First, you want to find out is there any distillation boundary. dB always goes low boiling to intermediate boiling, or intermediate boiling to high boiling. 62.1 in this region, 78.2, 78.5, 68.7. I can call this high boiling component 1 in this region. Okay, so LB to HP, that's RC residue curve. But LB to IB, this is distillation boundary. IB, LB to IB. In this region, RCM goes this way. So, you look at this, 62.1, 66.7, 70.8, 82.8, LB, IB. You can call this HB in region 2. So, LB to IB, LB to IB. This is also a distillation boundary, DB. How about this region? LB 62.1, 70.8, 78.2, 100. You can call this HP3. In this region, this is RC, DB. So now, are we drawing this diagram correctly? I will go through this again on page 46. In the middle, there's an equation. Enlarge it. Okay. First equation for a plot. Plug in the value on the right-hand side. Calculate N2. Two-component node. 2B binary azeotrope. N1 pure component node. N3 ternary azeotrope node, minimal boiling or high boiling. S3 three-component saddle. Okay? Once you get N2, you verify if your equation is correct. How many N2 it is? Your calculator plug into the second equation. Two-component node, binary azeotrope. You calculate if S2, two-component saddle, is the same as this equation. So, let's look at this back to 41. Are we doing this correctly? N2 equal, I need to load it. No. Okay. Smaller. All right. N2, 2 plus B minus N1 plus 2 times N3 plus 2 times S3 over 2. From the plot, three binary azeotrope minus N1, N, 3 plus 2 times 3-component node, that's exactly lowest boiling point of the whole system. 1 plus 2 times 3-component saddle, none, 0 over 2. So 3 minus 3, 2 plus 2 over 2. Calculated N2, 2-component node. S. This is calculated, okay? Now, you go to S2 equal B minus N2. Wait a minute, is this correct? 2 N1 3 is correct. 2 plus 3 1. This is 0. This is 0. 2 plus 2, 4. 4 divided by 2. But I got 3 saddles here. What's going on? Something wrong? Three minus 0. Good. Is that 0? Did I do something wrong? 2 plus 2 minus B is 3. M1, 3. 2. Which one?
Minus 2 times the N3.
Minus? Oh! You made my day. You made my day. 2 minus 2. 0 divided by 2, 0. You made my day. I was wondering what's going on. Calculated is 0, the plot is also 0. S2, 3, S2, plot, 3, big word. Thank you. All right? This is consistent. All right. Now, we're going to begin to have fun. Be creative. We're going to do some design problems. Look at section 3. The rest of this afternoon, purely design, fun, separation system, and unit operation in residue curve map. Chapter 3, page 2. If you have two components, A plus B, the mixing point is a feed in the middle. Now remember, B is represented by this length, about 30%. A, 70%. In terms of mole fraction of feed, A 0.7, B 0.3. Now, you mix feed with A, mixing point in the middle. This length is the feed. This is the seed. That's how we represent mixing, stream balance. Next page is a very useful tool. When you deal with vapor, liquid system, organic, aqueous, decanter is a very useful tool. You can separate organic layer, water layer, based on specific gravity difference. You look at this, feed, A, B. One is organic, rich. The other is water rich. Now, how do you see that in the triangle diagram? For the liquid attraction, okay, you have two liquid layers. It is the feed. You draw a tie line across the feed. This point represents, you look at this, water, benzene, ethanol, organic rich, we call it FO. B, closed water, water rich, FW. That's how you separate it. Okay? Now, distillation. Carbon 5, low boiling. Carbon 6, intermediate boiling. Carbon 7, highest boiling. No azeotrope. Your residue curve or you go through a distillation. Low boiling is your distillate. High boiling is your bottom. Now, this is what RC means. Now you will have a feed right here. You want to take out low boiling component first. We call this direct split. Carbon 5. So this is your distillate D. Meeting the boundary B. There's no azeotrope, so you get another column, carbon 6, carbon 7. That's how you separate it. Direct split. For the same problem, you want to get, look at it, low boiling, intermediate boiling, highest boiling. You want to get highest boiling at the bottom. That means your column passing through the feed is this line. This way, you can get another column, carbon 5, carbon 6. This is called indirect split, getting the highest boiling component bottom first. Okay? Now, if there's a feasible distillation, low boiling, intermediate boiling, highest boiling, you want to take out go to this line, IB as distillate. Just like you have three components. Carbon 5, carbon 6, carbon 7. You want to take this and distillate. You want to take both bottom. Can you do this? You cannot. You cannot. You want to get the intermediate component and distillate. Okay? So now, we are not going to talk about bow tie region, but go to 10, 11, 10. This is the tricky thing. Let me enlarge this diagram. You look at here, 61.8, 60.1, 50. Lowest boiling. In this region, 56.1, 65.5 IB, HB1. That is HB2. What's special about this? This is actually a distillation boundary. Your column, the dot, actually cross the distillation boundary. What's special? Both products are on the same side of distillation boundary. So, feed, product. Is this feasible? Yes. Do people use some trick to work on this? Let me give you better plot on the next page. If you look at here, this lowest boiling, this is the highest boiling. So, residue curve from now you have a feed below the distillation boundary. This is IB to HB. So this blue one that is the distillation boundary. When will this column be feasible? F, okay, distillate bottom, lowest boiling and highest boiling. Even though F is below the dB, distillate bottom, both are on the same side of the region, on the same residue curve. This is feasible, but not easy to control. Just for the fun of it, in case you need to do it, it's okay. Now, there are people teaching distillation boundary, bow tie region, and so on. You don't really need to know those in designing problem. Okay, first major application of what you learned so far. Go to section 5 first. Selection of solvent. even in your project, you will have to choose a solvent. What you have learned so far will give you what chemists cannot tell you. How do you create separation flow sheet? Okay? Chapter 5, page 1. Choosing a solvent and trainer, the same name. Find a feasible separation. Chemists using experiment. Chemists. Chemie. You need to think about both. And you can eliminate infeasible solvent very quickly by what you have learned so far. All right, chapter 5, page 2. You know the famous water ethanol azetrol 241 per headache. Water ethanol binary azetrol. You will have a feed here. Your column will stop. This is the distillate. That is the bottom. You cannot cross the azetrol to give you an ethanol. Okay? So you need a solvent. Is cyclohexane a good one? I don't like it too much. Too many distillation boundary, right? But here's the problem. Find good solvent, 15 of them, to separate ethanol mixture water. All of those. Are they good solvent? You can go to Aspen to find out pure component boiling point, binary azetrol, ternary azetrol. Aspen will give you that. So now, here is the trick. First real application to find a feasible solvent, a chemical engineering way. A, water ethanol is acetic acid, pure component boiling point, 118 degrees C. We know there's an azetrol here. So you go to Aspen, you find out 3 pure component boiling point plus azetrol. This is the feasible and good solvent. Why is that? 78.2 is the lowest boiling component. 118, highest boiling component. Intermediate. The good thing is there's no distillation boundary. If you have feet here, you have feet here, you have feet here, there's no distillation boundary. So that is a good potential solvent, a circle. How about B? 170.5, 178, lowest boiling, intermediate boiling, highest boiling. No, this is IB, this is low B. No distillation boundary. That is a good potential solvent. The next step is create a flow sheet. You want a number for binary agent show, pure component boiling point. Get on aspirin to get it. Now, C. Lowest boiling, intermediate boiling, high boiling 1, high boiling 2, intermediate boiling. This is LB to IB, DB. That means if the feed is here, you cannot get water. If feed is here, you cannot get ethanol. How do you do this? In the next section, we're going to learn how to cross the distillation boundary, get into this region, creating a new feed and giving you ethanol. But normal butanol as a solvent is a bad idea. I did not circle it. D. This is the potential solvent. You add the solvent, it also creates with ethanol a new agent show. You find a solvent creating a new agent show, troublemaker. Now, you look at this problem, not only new binary agent show, you create a ternary agent show. So let's look at it. 81.1, 78.2, 82.2. So in this region, high boiling 1, low boiling, intermediate boiling, Low boiling to intermediate boiling, that is a dB, distillation boundary. IB to HP, that is a distillation boundary. Now in this region, 78.2, low boiling, 81.1, intermediate boiling. This is high boiling 2. Intermediate to high boiling, that is a dB. On the top, low boiling, intermediate boiling, high boiling. This is dB. Chemist, wake up. You give me this solvent, you create a 3 distillation boundary, 1 extra boundary agent through, another extra ternary agent through. Chemist, sorry, you're fired. Right? Who want to do this? Do you understand the method to find feasible solvent? Once you find it, we're going to learn the next hour how to cross distillation boundary to do real design. Now, I do not need to continue this, right? This is feasible. This is no good, right? So, even though chemists derive from pure component boiling point, but they may have to do experiment to find binary agent or ternary agent, right? Or you go to the database to find it. 15 candidates, which you find is better. That is how we choose solvent. Okay? Linked together with flow sheet creation. So now, I'm going to skip the rest of chapter 5, and in the next hour, we'll do real separation flow sheet, okay? And this is real new, good stuff. You can apply to your project or your future industrial practice. Let's take a break.
Why not, right? I didn't really know what they did. One of them,
but it says that conversation they wanted their pellets, so we make pellets that are that small, or see how
so it's just fluid.
is that your
Is that like a main guy?
Yeah, no.
Yeah, my life. I just went all the time to street car, really. So look, just under that.
Like how much does it cost to
I'm done.
I think that's what it's gonna
Sometimes
sound.
you got the sweet, you got the fresh.
I mean, I think that would purely depend on the amount of energy. And it was.
What we could do for extrusion, we need to heat it at temperatures and just.
No, not necessarily.
Wasn't Keepster like supposedly kind of a lot of short players?
PET melts at 260 Celsius. They ran their extrusion step at 230.
What the end the quenching process? Quenching process, and what temperature do you have to heat it to?
So it has to be below 5 degrees.
What I mean, the heat of the process needs to be above blast resistor. What's concentration? So you can do that's kind of what I'm.
Well, we said that it should be the same in the process as well, because the higher above blast, put this way, if we were to go just above blast transition, we also need it there for super long.
After graduation, going up to the northeast for about.
If we were to even run to 30, plus 30 degrees below melting, you're gonna have to get that hot either way. It's just a matter of whether we
We're close to. What's going on?
So there's the stuff we talked about earlier.
The heating and then punching for the extrusion.
So there's heating, so if you heat.
I think I'll be fine.
Heat it and then quench it. It'd be
What's
What's quenching is
heat exchanger
process,
is down.
like process, process materials where you heat it up so that you can cool it really fast so it doesn't
Yeah.
crystallize.
Because even liquid form, it's completely amorphous.
Yeah.
And since
So extrusion does heat it. So extrusion heat it.
I thought he said extrusion was.
She's not even here. He's still in the bathroom. That's hilarious.
New meta.
The west.
So why are we choosing order?
No, he's saying it's not going to guard down. And then you will know cost of stuff. You can find out how much it costs to the process. Because one doesn't give a benefit over the other. You'll have a problem unless it's, if I'm not correct.
So, one solution is guaranteed basically.
Is the process.
And the other one is guaranteed about. Like, you're full on for an entire year.
And I don't know how expensive extrusion. But I don't know how expensive extrusion. It doesn't matter, especially you're doing
Anyway, okay, good. From what I'll do is I'll just write about both, and unless it would be bad, in the proposal, I'm just going to draw and say that as a civil design,
I mean, in theory, this is a
Okay, sit down. Let's finish this early so we can go home. Section 4 on residue curve map. How do you create separation system? Okay, here's the first challenge. Chapter 4, page 18. I want you to listen carefully, pay attention, so you can learn a few tricks. What is the problem with this? You have a component A, B, both are desired product, they have a binary agent control. Your boss give you a fee right here. This fee for this horizontal column, that will be the distillate bottom. The fee itself distillate is D1. Bottom B1, component A. You cannot get B. That is the purpose of finding on a trender or solvent. Now, when you use entrainer solvent, you do not really use 100%. You look at here, there's a point. That could be my solvent. What is composition of this solvent? Pure solvent is represented by this distance, about 85%, right? A, tiny amount. So now, you look at this D1. This is low balling. And the problem is this is a distillation boundary. Okay, this is distillation boundary. Low B, IB. How do we get a feasible flow sheet, create a new feed in this region to get your desired product? The way you do it, initially, you may not be familiar with the relationship between the two. But after you solve 10 problems more, you become familiar with the tricks. Okay? So, if I want to create the first column, giving me A, any fee in this region will work, even including F. So, and D1, B1, right? So B1, I draw the first column, D1. This D1 could be here, here. That's no good. I cannot cross the boundary. But I want to keep this a B1 as a product. So the first trick is, if I have a solvent This is a solvent recovery unit. Okay? Now, to get B, I will need another column, B. I will need a new feed in this region to give me B2, D2. Okay, the idea is, how do we create a new feed in this region? So, we have a rough idea of 3 column in sequence. How about the detail, the tricks? D3, B3. So, the way you do it, first, you find a point in this region, you call that B3 solvent rich. I want to recycle. So, the way you do it, original feed is A plus B. This point is trick number 1. Trick number 2, this B3. Okay? Recycle solvent plus feed. You get a new mixing point in the middle. You move the feed away from the straight line. You are no longer constrained by D1. That is the trick number 1. Okay? So now, the first column, I have a feed B3 plus F. I call that M1. This is M1. So, trick number 1, find your solvent, move the feed away from the back actor, azeotrope. Mix it, trick number 1. Together. Trick number 2, once I get M1, I know B1 is the product. How about D1? Always distill up to DB. What does that mean? I know B1, I know the feed. So now, this column stop at distillation boundary. I call this D1. Can you explain to me what's the reason for this column M1? We got B1. You fix D1 on the distillation boundary. What's the reason? Someone help me. Give me a good answer. Why do you put D1 there? If I put D1 here, it does nothing. I cannot cross the distillation boundary. You always distill up the distillation boundary. I got D1, right? Then I can find a stream to mix this, creating a new feed. That is the feed for the lovely B product. So, tricks always distill up to the distillation boundary. D1, right? Now, if I find the column to give me B2, I need a feed. How do I create this feed M2? How do I create a feed M2? So now, let's look at this carefully, and you go back to page 417. I can draw this more clearly so you won't be confused by this region. As long as I finish here, I come back, all right? I want to make sure this is B3. This is my F. So, I have my M1. So, M1 and this is my B1, M1. D1. That's exactly what I did, right? Now, D1. And I pick the solvent here, D3. Let's look at D3, D1. You get this straight line. So come back. D1. I set the solvent on this line. 85% E. So you mix those 2 points. This D1 solvent, okay? D1, D3, give me M2. M2. Okay? So, first column, distilling up to the boundary, give you a point to mix a stream. On this side, creating a new mixing point. That is a wonderful feed for this column. So we got B2. For this column, this is B2, that's D2. D2. This is the column. And this B2, that is all that part of B. Okay? How about D2? Just go to the solvent recovery unit. That is our D3, B3 column. Okay? Now, maybe you can see this better. You can see this better on color. Can you see it better? In this region. No confusion, right? You see here, D2? D2 is the feed to solvent recovery unit. D3 is my solvent. D1, M2. That is this lovely column. To summarize, yeah.
For column 2, how is it distilled through the
Column 2, I mentioned to you before, you can have a feed, your distillate bottom, as long as they are in the same side of distillation boundary, it works. Right? I mentioned to you before, in the previous chapter, okay? So, this third column, even though feed is here, on this side distillation boundary, but your RC on the same side distillation boundary, right? So this is no problem. To summarize, what it takes, move the feed up to avoid the aging shock, right? Mix this with solvent to get a mixing point. And this is your first column. Always distill to a distillation boundary. The reason is, once you mix with the solvent, you create a new feed, right? Next time, I put the feed in this region. See whether you can do something about it. Okay, if I put the feed, or if I have the feed here, what would you do? Think about that as a challenge. Do you understand this? All right. Indeed, 419. I gotta feed this area. How do I get a solution? Okay, now, previously, our feet was here. Now, feet is here. How do I cross the station boundary to get our product? So, just a little slightly different. You know you need a column to get B. That is a column. B1, D1. All right? I need a column. I need a column. And this problem, after you have solved 15 plus problem, you can mash the two in your thinking. The A column, in this case, B trade, D trade is the third one. Okay, you look at here. Solvent recovery give you the solvent, D2. D2 is about 85% E. So how do we do it? Feed you look at this problem, D2. Let's assume B3, right? I assume on the distillation boundary. I put D3 here. So this column give you an A product plus D3. We assume this on distillation boundary so that D3 later on you mix with the solvent recovery, you can create a new feed in this region. So, B3, that is A. I put D3 on distillation boundary, the same region as the last problem. Okay? Same region, last problem. So now, M2. So, D3, I want to mix this with a solvent. D2, D3, D2, D3, mix at M2 equal D2 plus D3. Now, what's M2? Where's the feed? D2, M2. M2 is here. Feed A plus B. Mixing together become a new feed. M1. M1. Now, this M1 move the feed above this azeotrope, right? So I can now, this column is this column. What's D1? Top. D1 become the feed of solvent recovery unit. D1, right here, we draw a line D2. And B2, now, just D1, what do you stop? There are a few possibilities here. A, B. Some are good, some no good. Okay? Which one is good? You look at this, D1 produce D2, B2. So, this feed is here. Both products, I think B2, which one is better? I think. Okay, let's look at this. 1, step 1. 2, D3. I'm assuming D3, B3 on a straight line, step 2. Step 3, D3, D2, M2. Step 4, M2, feed, M1. Step 5, where do you fix this B2? Okay? Fine. Assume B2. D1, okay, B2. This D1 in the middle, this D1 in the middle is on the left of distillation boundary, okay? This, I think, 5, 6, 7. I think this point. Okay. D1, that's a feed. And this point, B2, D2, are both on this side to the right of the distillation boundary. That is feasible. So, there are 2 points here. And B2B is better, a better location. Okay? B2A is not good. B2B, D1 feed on this boundary, but 2 products are all on this side of distillation boundary. This is a little tricky. If I have a color plot, I can show better. I don't have one. Now, with this as background, I want you to think about a problem. 19A. Let's look at this, too big. 80.2, 77.6, 69. So, lowest boiling ternary azeotrope. So, 69.1, 69.6, in this region, that is intermediate boiling. Sorry, this gives you a constraint. $69.1, 77.6, 80.8. High boiling, intermediate boiling. So, distillation boundary curved. How about this one? In this region, 69.1, 71.8, 80.2. Now, this one, low boiling. On the top, that is intermediate boiling. And this, Unfortunately, about in this region, there's a high boiling tube. This is intermediate boiling, lowest boiling. My goodness. A little tricky, right? 69.1, 82. This is RC. So, ternary azeotrope, 69.1. is the lowest boiling of the whole system. Distillate. Okay? Now, a fee is here. Constrained by this azeotrope. Our goal is to separate cyclohexane, benzene, but you cannot get it if your fee is here, low boiling, high boiling, distillate, bottom. You cannot cross this distillation boundary to get A. So that is a troublemaker. Our goal is to get A and B as pure product, overcoming this azeotrope. Now, this whole thing is not difficult. Phi. A, right here. You look at this, intermediate boiling, low boiling, intermediate boiling. So, right. So, how do I do it? I want to find B. I want to find a drinking point D1. Okay? And this will be a column, bottom, overhead, bottom. What do you do by D1? I can make that at the feet. I told you before, D1 below the distillation boundary D2 and B2. So, wait a minute, is this distillation boundary? 69. Low spawn. That's distillation bond, that's correct. So, yeah, this is what we did in the beginning. Let me show to you that here, right here, you can have a fee, right? 311. You can have a column fee on one side of the distillation boundary, product on the other side, as long as they are on the same residue curve. Page 311. So, this is page 311. D2A. Is that tricky? All right. Now, let me see. I think I'm going to cover this famous problem. Who is your project advisor? Eastman Chemical. What is the tricky problem? Phenol, water, normal butanol, azetrol, Dr. Culver made himself famous. He solved this problem, got Eastman Chemical patent, implement this process. What is the problem with this? How do you do this? I'm going to explain that on Monday, okay? Famous problem. That's it for today.
I wrote a paragraph on it.